Okay, while we're waiting for the other people to get started, if you want, you can share your screen. So on the left side, click screen share, share your screen so everyone can see what you're typing and how you're configuring. That'll make it easier if you run into trouble, and we can kind of look over your shoulder and see what's happening. So while we're waiting, just to give you a brief overview of what's going to happen in the next 4 weeks, well, this week and the next 3 weeks. We're going to cover this to the standards of the new CCNA 2013 exam. This is the 100 and the 200 exams. It's the ICND 1 and ICND 2. It's going to be a little different, a little bit more in depth than the previous exams. Now, what you have to do is in the first exam, you're going to do regular OSPF. It's going to be OSPF and troubleshooting. In the second exam, ICND Part 2, you're now expected to know multi-area OSPF, and this is for CCNA. So what you had to learn mostly for CCNP, now that's going to be in CCNA instead. Also, they're going to hit you more with troubleshooting. They're going to hit you more with verification, what things going wrong, that type of stuff. So they took out RIP, but they made OSPF a lot more in-depth. So just a little heads up for you guys who will be taking the new version of CCNA. I forget when it actually becomes live, but when it does become live, that's what you're going to be hit with. So pretty easy. This particular meeting, we're going to cover OSPF neighborships, putting interfaces into OSPF, the different ways we could do it, seeing how we form neighbors, and we're going to start looking into the OSPF database. So once you have GNS3 up and running, we're going to add in 2 routers. So on the left-hand side, click on that router icon, 3700, and drag in 2 routers. And just for this meeting, 2 routers is all we're dealing with. And if you want to scroll in, hold down Control and use your mouse wheel to zoom in. We're going to connect them together. On the left-hand side, you've got this little end of the Ethernet cable. Turns in your crosshair, click on R1, fast 00, R2, fast 00. And then just click on the stop sign to get your cursor back. And just to add in some notes so you don't get confused, click on this notepad thing in the upper, kind of like the upper menu bar there. And then click somewhere near the line, and we're going to type in 10, 10, 12, X /24. This is just a text note for us so that when we're configuring, we know that the one side's going to be 10, 10, 12, 1. The other side's going to be 10, 10, 12, 2. Going to make another note. Click on this notepad deal. Type in LO0, stands for loopback 0. And R1's going to be 1111/32. And you guessed it, R2 is going to have the same deal, except his is going to be 2222/32. And if you want to save this somewhere, you can. Just File, Save Project As, and you could save it as like, 2 router topology, my first topology, however you want to call it. Okay, anyone need any more time with this? So we're just setting up our basic topology yet. We actually haven't started yet, but if you have everything up like this, as you see on my screen, just click on play and then click on start a console and console to all devices. Please mute your mic. Thank you. And I'm just going to change my font on my end so that you guys can see it a little bit more clearly. Okay, so console windows are up. So for those of you who just joined us right now, all we're doing, we've just made a two router topology, R1 and R2. Haven't put in the IPs yet, but our notes are 10.10.12x/24, loopback 0, all 1/32, loopback 0 for R2, all 2s/32. Fire up your consoles, and it should look like that. Okay, so first order of business, we are going to put on the IP addresses on our interfaces. So on router 1, interface fast 0, IP address 10.10.12.1. Nothing too spectacular on that guy, and no shut. Configure your IP address on R2. And after you no shut both sides, just ping the other end just to make sure you have hop-top connectivity. If you have a good ping, then both sides are no shut or good. I like that typo there. That was awesome. Okay, so it looks like you guys have a good ping. So basically, generally I type faster than most of you. So after I'm done, what I do is I click through your windows and I just see how far along you guys are, and I wait for the majority of people to finish up. So this is why you should share your screen for those of you who aren't sharing your screen, because it helps us troubleshoot things much easier. Okay, we got two routers. They're not running anything. All it is the interface is no shut. We have an IP address on there. Not too big of a deal. We learned last week, or it was either last week or the week before, about static routes, how to get basic connectivity from one end to the other. And that works well as long as you're in a small group, a small network, and things don't change, because we manually have to type these things in. So the problem with the static route is that if I add extra network, so let's say I'm an ISP, I add another Ethernet link here, and there's other computers, I'm going to have to tell all my other routers in my network, assuming I have like R3, R4, or whatever, I'm going to have to put in static routes everywhere. And this is definitely not a scalable solution. So what we want to do is we want to use a dynamic protocol, something that we configure very simply, and that if something happens, we can reroute other ways. So what I mean by that is, if we have a network kind of like in a square topology here, it's kind of a jacked up square, but whatever. And so let's say we want to get to a rack of servers right here. This link goes down. We want a protocol to be able to detect a failure here and then be able to start sending traffic around the other way. Right? We want this network to be resilient, fault tolerant, and I don't want to have some guy standing over the router always typing commands in. I guess you could hire someone for like minimum wage and do that, but that's kind of dumb. So OSPF allows us to do that. OSPF will learn about new networks and will be able to route around stuff. Now normally OSPF, you can configure it with 2 lines. If you just want OSPF to work, 2 lines will do it. And we're going to actually start off with that because I want you to see how it works, how simple it can be. So let's do that. Let's get back your console window. So R1, oops, router, whoa, router, OSPF 1. What this command does is it's going to start the OSPF process, and it's going to tell the router, oh, by the way, I'm going to have more OSPF commands to type in just a second. And when you hit enter, you can see it drops your config down to config-router. Now this number at the end of router OSPF, that's a process number. You can pick 1 through whatever. You can also use the 4 dotted decimal format. doesn't really matter what number you use. Most of the time you're going to use router OSPF 1. Yeah, Kevin, so yeah, you'll just probably have to troubleshoot that on your end. Can everyone else hear my audio perfectly or okay? All right. So the one thing that's lacking with Google Hangouts versus, let's say, Skype. So Skype has that call, that test call feature where you can make sure your mic and speakers are working correctly. It would be really nice if Google Hangouts had something similar, so that before you go into the room, that you're assured that everything's okay. But yeah, it's probably your speaker settings, speakers, volume, anything like that. Okay, so router 1, router OSPF 1, next line 0000, and I'll explain what all of this means. And then we'll do 255, 255, 255, 255, area 0. So that's our two lines to get OSPF up and running on router 1. And then you'll just type the same thing in on router 2. So go over to router 2, router OSPF 1, network 0000, 255, 255, 255, 255, area 0. This is the easiest OSPF config that you could possibly do. And then we'll end out of there. Now you see nothing's happening just yet, but if we show IP OSPF neighbor, we're going to see that we have seen a neighbor over here, 10.10.12.1. So it's router 1. We're in a two-way state, druther. So what this means is we've shaken hands and we've started talking to each other. We haven't agreed with everything just yet, but at least we've seen each other. And now you can see that we get a message saying loading to full. What this means is you can think of it as two businessmen meeting each other. The two-way state is they've shaken hands, but they haven't actually traded business cards or anything like that. But once we get into the full state, what we know here is that we've traded our business cards, we've looked at them, and now we know all the information about the other guy. And by all information, we know the other guy's routes and links. So very easy config. Now, of course, Cisco is not going to ask you such a simple question, just start OSPF on two routers and use these two lines. That's not how it works. But if you have a small network, 3-4 routers, and you have nothing special, starting OSPF, two lines, you could get this done in about 30 seconds, if you didn't want any optimizations. But of course, we are going to do some optimizations after we do some show commands. So let's go to router 1. And on router 1, what we have is show commands. Everything's going to be show IP OSPF something. Right, and you see if you do a question mark, you'll have lots and lots of stuff. But you already know about show IP OSPF neighbor. That basically says, okay, who's my neighbor? Show IP OSPF interface. This shows what interface your routing protocol is running on. So what happens here is when you start OSPF, and OSPF started on, let's say, this is fast00. OSPF is periodically sending out hello packets, and it's also listening for OSPF packets. So it's expecting OSPF to come in, and it's sending OSPF out. We can actually see the real time of that if we debug IP OSPF hello. So debug IP OSPF hello. And you'll see your timestamps here. So if you look at my timestamps, 38 seconds, 48 seconds, and if we predict 58 seconds, so we're sending out hellos, We're also receiving them every 10 seconds from the other guy. You can see that we're sending out hellos to a multicast address, 224.0.0.5. We're receiving a hello from the other side, our next hop, which is 10.10.12.2. That's the fast Ethernet link on the other side. So just looking at your debugs, how often are these hellos being sent? So how often are the hellos being sent? Every 10 seconds. You can see that with looking at the debugs. So Jerry has a question, why a multicast address? That's actually when OSPF was invented, we expected that this link could have lots of, they could have lots of devices here. I don't know what the heck that big square is, but lots of devices there. So there's a possibility that a lot of things could answer back. It's not just routers or IP-enabled switches, layer 3 switches. It could be servers because Linux understands OSPF. OSPF is an open protocol. So they wanted to agree on some IP address that people could answer back, because we don't want one company to have one IP address for OSPF and another company to have a different IP. We want to agree on some standard. So 224.0.0.5 is one address and 224.0.0.6 is another address. That's the standard that they agreed on. It's using multicast because we're on a broadcast enabled interface. Ethernet's considered broadcast, but we can change that later into a unicast if we want. So we have our debugs on. We see that we are receiving hellos from the other side. So what do you think would happen if I killed OSPF on router 2? Would I continue receiving hellos from the other side, or would the hellos stop? They should stop, right? So let's try that out. Keep the debugs running on router 1. Go over to router 2. Now we have a couple ways of doing this. We could kill the interface, but that's like the nuclear option, right? So what we could do here is conft no router OSPF1, and that's going to kill OSPF. It's going to do that. We'll take a look at R1. And you can see we're still sending it out, but we don't have any more lines saying that we have received a hello from the other side. Okay, does that make sense to everyone? That should be pretty basic. You kill OSPF, it's going to stop sending out hellos. Now you'll see something interesting. I waited, it was about 40 seconds. So if you look up here on mine, I stopped my last hello, I got at 8 seconds. And then at about 57 seconds, so about 40 to 50 seconds later, the neighbor went down. According to R1 side, I'm basically saying, oh, the neighbor's dead. Dead time expired. So I'm sending out hellos every 10 seconds, But at 40 seconds, basically I'm saying, well, that guy's dead. And we can see that if we go show IP OSPF interface on R1, and you'll see right here, timer intervals, hello 10 seconds, dead of 40 seconds. Now, how many of you think 40 seconds is kind of a long time in the network world? Yeah, 40 seconds, your calls have dropped, transmissions have dropped, people are hitting F5 on the web page. You know, it's horrible. So we're going to change that, but first, before we change that, let's go back to R2. We're going to start OSPF again. And this time we're gonna be a little bit smarter than before. So before we did this, network all zeros, 255, 255, you know, we did all that. Now what that does is it says every interface, just chuck it into OSPF. That's good in the sense that if you don't care, if you just want that router to be in OSPF, it'll work. But if this router is connected to other protocols, probably not so great. So we want to be exact. So the way we want to be exact is this. We want to put in the exact IP address of that interface, so 10.10.12.2, and to match it exactly, it's 4 zeros. Now the 4 zeros right here mean if you're used to a regular subnet mask, it's basically saying all 255, so match it exactly. Area 0. As soon as you hit enter there, you can see the other side comes up. Okay, we go back to R1, do a UAll to stop those debugs for now. We're going to turn them back on later. So we want to change this 10 seconds and 40 seconds. Once again, if you show IP OSPF interface, you get the hello and dead timers. If you kind of want the shortcut, what you could do here is show IP OSPF interface, and you could filter out the output. You add a pipe symbol, pipe I, and then the word dead with a capital D. And if you do that, once you hit enter, you'll just get in that particular line. That way you don't have to hunt through all this output. So we want to change this, and the way to change it is we actually have to go on the interface itself, because this is an interface, a specific command. So conft interface pass 00, and it's going to be IP OSPF hello interval. Now we're going to change our hellos, and we're going to see what happens to the dead timer. So we're sending hellos every 10 seconds. If we miss 4 of them, then we're going to be considered down. So what's better than 10 seconds? Give me a number. What sounds reasonable? 5 is reasonable, 2 is reasonable. Let's go with 2. 2 sounds pretty good. So IP OSPF hello interval 2, and nothing comes after that. We hit enter. End out of there. Now if we debug IP OSPF hello, you could see immediately that you are sending hellos every 2 seconds, and look what you got here. Do a UAll here. You have a new message. You're definitely sending every 2 seconds, but how many of you get this message? You received a hello from 12.2, and it's saying mismatched hello parameters. How many of you see that in your debug? So you set your side to 2 seconds for each hello. What's the other side still set to? 10 seconds. Your 2 seconds doesn't match to 10 seconds. So, and eventually what you see on R2 is neighbor went down. Neighbor died. So what does that tell you about whether things have to match? They have to match or else the neighborship dies. It also tells you this hello and dead timer, are those values sent in the hello packet? They have to be, or else you wouldn't be able to detect them. So the hello and dead time are stuck in this packet. That's what you're sending out. The other side looks at it and goes, oh, okay, well, you have set to 10 seconds. I have it set to 2. We don't match. Drop. Don't like you as a neighbor. So let's go back to R1. Let's show IP OSPF interface. So we see here, let's filter it out just for kicks. We remember setting our hello to 2. I don't remember setting a dead timer, but it set it to 8. So what did the router automatically do for us? Yeah, it times it by 4. So it helped you out because it goes, well, you'll probably be okay if you miss 2. 2 is okay, 3 is okay, but if you miss 4 of them, I'll take you out. So we know our neighbor is down. If we show IP OSPF neighbor, we don't have a neighbor. Neighbor's dropped off. So if I go to the other side and set his hello to 2, what do you think is going to happen? It's going to come back up. Yeah. So let's go to R2, interface fast00, IP OSPF hello 2. Pretty much instant, boom, we're back up. So you can see how I'm doing this. All I'm doing is taking 2 routers, I'm running some debugs, I'm changing one thing at a time, and just seeing how one side reacts. All I'm doing. And how many of you have seen the video series that I did? It's on the YouTube channel. I think I called it OSPF for babies or something like that. Basically, each video is less than 5 minutes. This is exactly what I'm doing. So let's go back to R1, go back to that interface fast00. So before we did IP OSPF hello interval, we changed the hello interval. We can actually directly change the dead interval. I'll explain what this minimal setting is later, but let's change the dead interval to, let's say 10 seconds. Right, nothing comes after it, so IP OSPF dead interval. And I've changed the dead interval, my neighbor's gone down. So you can see not only does the hello interval have to match, the dead interval has to match as well. Hello and dead interval. Now if we hit the up arrow a couple times, show IP OSPF interface pipe I dead, you'll see that dead interval is set to 10, the hello interval stayed at 2. So when you go one way, when you set the hello interval, it automatically does your dead interval 4 times of that. So if you set your hello at 5, your dead's going to be 5 times 4, which is 20. If you set your hello at 10, dead interval is automatically going to go to 40. But when you set your dead interval directly, like we just did, hello doesn't change at all. Okay, so if you've been reading your Cisco Press book or Todd Lamley book, you've probably read this and gone, oh, okay. But until you actually do it, you won't get it. It's always better to lab it a couple times, and then it's going to stick. Let's go to R2, change the dead interval to match. That way we can get our neighbor back up. IP OSPF dead interval 10. And OSPF is back up. Now 10 seconds is still a long time, still a while. So now what we're going to do is we're going to do this. We're going to say that if you don't hear from the other side in 1 second, I'm going to consider it down. So I will tolerate up to 1 second of non-connectivity, and then I'm going to assume that something is wrong. So here we're being really, really strict about connectivity. And the way we do that is go to R1, conf T, go back to the interface. And this way it's kind of backwards. We're not doing the hello interval first, we're doing the dead interval. And in this case right here, setting the dead interval will change the hello interval. So this is a kind of an exception to the rule. So IP OSPF dead interval, if you do a question mark, you'll see the word minimal. What minimal says is I'm going to set it to 1 second. I'm willing to tolerate 1 second of disconnect. And here's what's interesting. Do a question mark, it's asking you for hello multiplier. Question mark, how many hellos do you want to send in 1 second? Now if you're on a slow computer and you're running GNS3, please do not pick 20. So here we will pick 3, and as it says right there, you're going to shoot 3 hellos a second. We'll end out of there. My neighbor went down, and the reason my neighbor went down is my settings don't match. So go over to R2, IP OSPF, dead interval minimal, hello multiplier 3. So both sides now are sending hellos 3 times a second. If you run your debug, it's going to look crazy. We're having fun with that debug. And type in you all really quick to stop that, or else it's gonna be a bad day for you. So here's a question. Why would you do this? Why would you want such a fast turnover on connectivity? Why would you want to send 3 hellos a second? Fast convergence, yes, but what industries would want that fast of convergence? Banking would be good, yeah. ISP would be good. Netflix, any type of video, yeah. You definitely want that. I'm thinking, yeah, anything financial. So here we could definitely do that. So what you saw with the mismatched hello parameters and the dead interval, that's part of troubleshooting. You could have everything set up correctly, but it's off by like a second and the neighborship won't come up. That could be something that you could troubleshoot. Okay, let's add some loopbacks. So in R1 we still have router OSPF1, network all zeros, all 255.0.0. We're throwing everything into OSPF. And we can see that show, let's actually look at a running config, show run. And you hit space a couple times. And that is our configuration. Router OSPF1, network all zeros, all 255s, area 0. So let's add a loopback to router 1. So conf t interface loopback 0, IP address 1111, 255, 255, 255, 255. He's going to be chucked into OSPF. If you want, you could also add in loopback 1, IP address 8888, 255, 255, 255, 255. The IP address doesn't really matter on the second one, just make anything. But in my case, I like all 8s, all 255s. And what you'll see is if you show IP OSPF interface, you're going to see all the details of everything that's running OSPF, and loopback 0 and loopback 1 is up there. Now that's sometimes too much detail. You're maybe not that concerned about it. So if you hit the up arrow and add a BR at the end for brief, it'll give you a nicer formatted one. It's basically, here are the interfaces, here's the areas, here's the IP. So what's cool about OSPF, it's dynamic. It automatically took these interfaces, started OSPF on it. And it's also shot the information across to R2. And now R2 knows how to get to those loopbacks. So if we go to R2 and show IP route, you'll see that we have 2 O routes. O means OSPF gave them to you. And so that's all 1s and all 8s. You can clean up that output a little bit, show IP route OSPF. So just give me the OSPF routes. And you can go even further, show IP OSPF route pipe I, capital O. And that will give you a really nice output. Just two clean lines like that. So I have it in my routing table. If I ping all 1s, it comes back. If I ping all 8s, it comes back. And this is all because router 1 told router 2 in an OSPF update basically says, hey, I know of these links. Here you go. Here's how to get to them. Here's the next hop on how to get to them. And that's known, the database that stores that is the OSPF database, and we can actually see what's in there. Show IP OSPF database. Okay, we got a couple entries there. So the link ID in the advertising router, for now, you'll learn that this is slightly different in CCNP and CCIE, but for now just believe that 10.10.12.1 is router 1. 10.10.12.2 means it's coming from router 2. Now this ID, we can change this because sometimes 10.10.12.1 may not be the best thing, because you could have IP addresses on your interfaces. It's pulling this from your highest interface that was on at the time when you started OSPF. And usually it's going to pull the order is the highest IP address on your physical interfaces, and then your highest IP address from your loopback interfaces. But you can see right here, why isn't it all 8s? And the reason is we started OSPF way before we had our loopbacks. So that's why it picked 10.10.12.1 to start with. Now if we look across, we see that, okay, we got, that's router 1. We've known about router 1 that long. That was the last update when things changed. 3. It knows about 3 links. In this particular, we call it an LSA, link state advertisement. All an LSA is just think of a business card with different phone numbers on it, different addresses on it. So you could think of the router as the businessman. The businessman just handed you a card, an LSA. It's got information about 3 different locations. We can get more detail about that guy, that LSA, what's on the card, by show IP OSPF database. This is known as a LSA type 1, which is a router LSA. This is the basic one. Router. And if we just hit enter there, we're going to get all of them, the both of them. But if we want to get a particular LSA coming from a particular router, we could do 10.10.12.1. So show me the router LSA coming from router 10.10.12.1. And we hit enter, and if you scroll through, you'll get to a number of links, and you get these 3 entries, which correspond to the 3 entries, your 3 interfaces. So stub network, whenever you see stub network, that's probably coming from a loopback. That was loopback all 8s. We got all 1s, that's the other loopback. Transit network, 10.10.12.2. That's the guy that you're using to get to router 1. Your links are transiting through 10.10.12.2, getting to the other side. So it's saying 10.10.12.2, 10.10.12.1, that's other side. That's how you're going to hit these other guys. Now if you show IP OSPF database, you're going to see this entry right here. This is a network link state. So on that Ethernet link, someone has been picked to be kind of like the master. He's in charge of sending these LSAs to everyone else. And in our case here, 10.10.12.2, which is router 2, has been picked as what's called a designated router. In actuality, it doesn't really matter that much whether it's router 1 or router 2, because fast Ethernet, if it's just 2 routers, we don't really care. And the reason that router 2 probably won is when we started OSPF, router 2 had the higher IP address. Okay, any questions up until this point? We're just kind of looking through some show output. We have a very simple OSPF network. Okay, we have a question from John. Can one router send the hello and dead intervals out to other routers? So are you asking it this way? So are you saying if router 3 is out here, are you saying that will router 1 send the hello and dead intervals from router 2 to router 3? Like passing through? Okay, so the hello and dead intervals are done on a hop-by-hop basis. So this DR, this master, so let's say R1 is the DR and R2 is the BDR. It's not so much the hello and dead intervals, it's more of the LSAs, who's in charge. So the reason for all this is back in the days, we could have had other routers out here. And if there was no master, what would happen is, as soon as there's an update, so let's say R2 adds a loop back right here. This whole network goes crazy because everyone starts updating everyone and it just goes nuts. So a DR is basically a guy he's like the MC at the party or the main guy at the party. He's shouting out instructions to everyone else and everyone else is listening. So in this case right here, if R2 makes a loop back, R2 sends the LSA straight to R1, and then R1 is in charge of shooting it out to everyone else. So it's one guy talking. The hello and dead intervals, that's still done from router to router. Okay, so no one's getting hello and dead interval settings. It's not like if you're the DR and your hello is 10 and your dead is 40, you're not going to force that on other people. It's still, if it doesn't match, the thing goes down. So you're only the master, you're only the designated router for LSA information, nothing else. Okay, let's see what happens if we reset OSPF. We basically clear it out. So on R2, let's clear IP OSPF process. Enter. And type in yes. And R1, clear IP OSPF process. Yes. So basically we are kicking everything over. And let's see if anything has changed. If we're on R2, show IP OSPF database. Nothing changed too much. Let's show IP OSPF neighbor on R2. Okay, neighbor 10.10.12.1, that still looks the same. So you can see that if I look at both sides, show IP OSPF, that's another command that you should know. Show IP OSPF. You'll see right here. I'm running OSPF 1 and I have the ID of 10.10.12.1. If I look over at R2, show IP OSPF, it says I'm running OSPF with the ID of 10.10.12.2. So if you read your books, you'll see that it'll say your router ID is your highest IP address on a physical interface. If you have a loopback, it'll be the highest IP address of the loopback. Here we're kind of stuck. It's stuck at 10.10.12.1. Even after doing a clear. So what we're going to do now is we're going to really kick over OSPF. So the way we do that is on router 1, no router OSPF 1. So it's really cleared it out. And then we'll go back in, router OSPF 1, network all zeros, and you could, the proper way is 255s, 255s, but you can cheat. If you just do 4 zeros, area 0, that will also work. And if you show run, you'll see that it changed the second set of all zeros to 255s. Alright, so you can type in all zeros, that's not a problem. You just changed it to 255s. Now if they ask you in the test, what's the answer? Use the 255 answer. Even though in real life it's all zeros, use the 255. This is just Cisco helping you out. Okay, so now on router 1, if you show IP OSPF, your router ID has changed to all 8s. And let's see if it looks any different on R2 side. Show IP OSPF neighbor. All 8, so that's good. So when you show IP OSPF neighbor, we're doing this in R2, we see that we're in a full state, which means we've traded all of our information, and we're in the other side is in the BDR mode, backup designated router. So always remember, when you show IP OSPF neighbor, you're looking at the other guy. The other guy is the BDR. So if the other guy is the BDR, most likely R2 is the what? DR, correct. This sometimes trips up students because you have to look at it from a different perspective. Now, if you want to see what your side looks like, it's show IP OSPF interface brief, and this will show you that on your side, your fast Ethernet 00 is DR. So the naming is kind of weird. Even though it's called designated router, the designated router can be different depending on which link you're looking at. So you can have 2 Ethernet interfaces. On one interface you could be the DR, on the other interface you could be the BDR. So it's not done for the entire network, it's done per interface. And graphically what that could be is, if you got another router here, so on this particular side you could be the DR, on that particular side your interface could be on the BDR designation. So it's not done per network like you would think. Like designated router sounds like, oh, it's the designated router for the entire network. It's not how it is. It's designated router for this link. So it's on a link by link basis. Okay. Any questions up until this point? All right, let's make a loop back on router 2. So router OSPF 1. Oh, sorry. Interface loopback 0. IP address all 2s, all 255s. Boom. Now you'll notice in this case right here, if I go back to R1 and show IP route OSPF, I don't have anything for R2. I don't have any OSPF routes. Now I can just do a quick gut check just to make sure OSPF is running on my computer or on my router, show IP protocols, and we have OSPF running, so that's good. Let's show IP OSPF interface, and we have fast00, you know, everything's good. So OSPF is running, check number 1. Check number 2, do I have interfaces in OSPF? Check number 3, do I have neighbors? Show IP OSPF neighbor, I have a neighbor. So is OSPF running? Do I have my interface in OSPF? Do I see a neighbor? Remember those 3 things for CCNA. That's probably going to get you a majority of your OSPF troubleshooting verification questions. So it looks like my side is good. I should be receiving anything that R2 is sending. So whenever you're in this situation, always ask yourself, it's possible that the other side may not be sending me anything. You know, I'm neighbored up. I'm definitely seeing hellos because I have a neighborship. Maybe I'm not seeing the routing information, the database information. So show IP OSPF database. And right off the bat, you'll see that for R2, okay, link count of 1. Okay, let's show IP OSPF database router 10.10.12.2. Let's see what's in that LSA or that business card. Router 2 is telling me how to get to this network right here. It's basically saying 10.10.12.2. I'm getting to the other side. What is router 2 not telling me? So I made a loopback with all 2s. Do you see that anywhere in this LSA? It's not there, right? So router 2 is not telling me this information in OSPF. So you don't have it in router 1's routing table because router 2 is not putting it into OSPF. We could go back to router 2, show IP OSPF interface brief. So we do a quick gut check. Are we even putting loopback 0 into OSPF? We're putting fast00 in there, but we're not putting loopback 0 in there. And why is that? Who remembers what we did on router 2? On router 2 we did a exact match. So if we show run, okay, right here. We did router OSPF 1, 10.10.12.2. We matched the fast00 exactly, right? So your router did exactly what it was told to. It just matched the interface. So now let's match the loopback. So there's 2 ways of putting an interface into OSPF. So router 2 conf t, router OSPF 1. You can use the network statement. So we could do 2222, 255, 255, 255.255, area 0. That works. Or you could go directly in their interface. And I kind of prefer it this way. So you go right into interface loopback 0, IP, OSPF 1, chuck it into area 0. That's the direct approach. Just go into the interface and say turn OSPF on here. Now we verify both, stay on R2, show IP OSPF interface brief. We got a loop back in OSPF. So if R2 has the loopback in OSPF, R2 is going to throw that information in the LSA. If I go back to R1 and show IP OSPF database, will that entry for R2, will it have some extra information if I look at it on R1? Will something have been added? Will something be different? Yeah, so we show IP OSPF database. So before the link count was 1, now the link count is 2. Something's been added. Now if you have half a brain, you could probably guess that that thing that was added was 2.2.2.2. And so let's show IP OSPF database, router 10.10.12.2. Look at that. 2222, subnet mask all 255s. That was added. And if we ping it, or even before we ping it, let's show IP route OSPF. Got it in there. Ping all 2s, we get a successful ping back. Right, so knowing what happens, being able to explain what happens when you add one side, it's going to be chucked into your OSPF interfaces, then it's going to be chucked in the database, the LSA goes over to the other router. The other router is going to look at the database, import that information into the routing table, and now it's going to be able to ping over. Now I want you to see something. Kind of put your windows side by side. Show IP OSPF database on router 1. Show IP OSPF database on router 2. Check out the information. Link ID, all 8s. Link ID, all 8s. We'll ignore the age for now. Sequence, there's a 3 there. Sequence, there's a 3 there. Checksum, blah 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 ECF, checksum, blah 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 ECF. Link 3, 3. Next line over, everything's the same except age. Next line over, everything's the same except age. The databases are the same. All your routers in the same area have the same information. Just like if you go to Google Maps and look up Las Vegas, and I go to Google Maps and I look up Las Vegas, both of us are going to get the same information. It's going to be the same map. Now how we decide on how to get to a certain destination, that's up to us. So in OSPF, all your routers in the same area, they get the same map, they get the same database, Microsoft, that's Google. I actually like Bing. Bing Maps looks pretty cool. So we have the same map. The routers both have the same map of all the routes, of all the links, but how the routers get there is different. And the way we decide on how to get there is by comparing cost, lowest cost. So just like when you drive around on the freeway and you're deciding what's the fastest way for me to get to work. So I'm going to use the Southern California example. We have the 10 freeway. We have the 60 freeway. 605. We have another freeway out here. All right. So I'm way out in the boondocks, like 60 miles east of 60 miles east of LA, right? So I'm way the heck off this map. I'm trying to decide the best way of getting to work, which is down here. Now, when a human being decides how to get to a place, what are the criteria that I'm using? What things come into the decision when I start my drive in the morning and I want to go from the upper right-hand corner to my work at the bottom left-hand corner? Traffic, right? Is the freeway on the 10, is it clogged up? Speed limit. Can I go 55 here? Is it 75 here? What's another thing that comes into play? Distance, exactly. Distance, complexity. So distance meaning, well, if this guy right here is 60 miles and this guy, a big detour around, is 80 miles, I should probably take 60 over 80, right? Complexity. How many junctions am I going through? Most people would probably want to just take a straight shot. Maybe it might be like maybe a couple miles more, but if it's a straight shot, a lot of people will go for that. Okay, so human beings take a lot of this information and they make a decision. That would probably be how EIGRP works. The way a human being thinks is sort of like how EIGRP figures things out. There's a lot of crap in there. Most of it's turned off, but you have the capability to do that. OSPF only looks at one thing. It looks at speed. So speed is, are we 100 megalink? Are we 1 gigabit? Are we 10 gigabit? Now by default it won't actually differentiate between the higher ones, but you can actually change that. So speed, the faster the speed, the lower the cost. And that's all it's looking at. It's not looking at distance or traffic or anything like that. We're basically saying if you have OSPF set correctly, 100 meg link beats a 10 meg link. 1 gig link beats 100 meg link. That's all we're looking at. So in the cost, when we actually look at this, you're not actually going to see 100 meg, 1 gig. It's going to crunch this down into a number. And let's actually see what number that crunches down to. If we go to R1, show IP OSPF interface brief, you'll see right here, your loopbacks have a cost of 1. Really can't get much lower than a 1. And your fast Ethernet link has a cost of 10. Right? So what we got here is, whoa, this costs 10, and our 2 loopbacks cost 1. So if I'm starting my journey at R2, for me to decide on how to get there. Now, in this example, it's silly because I only have one way of getting there, but imagine if, you know, I was in a triangle and there were 3 routers here. But for me to decide the total cost of getting to a destination is very easy. I just look at the path and I say, okay, well, this link right here is 10. That link right there is 1. 10 plus 1 is 11. And we should be able to see that if we go to R2, show IP route, and let's see, let's clean that up a bit. Show IP route OSPF, pipe I, capital O. If I want to get to that loop back or that loop back, it's, boom, this second thing here. That 110 is the administrative distance. We'll talk about that later. But that is a cost of 11. I just added up. 10 plus 1, 11. I can change the cost. Now this is outbound, by the way, so R2 looked at its outbound cost here, and we got that by show IP OSPF interface brief. Going out fast 00, it cost me 10. Now you may be wondering to yourself, if you've been reading your Cisco press books, you may be asking, well, Humphrey, I always read that fast Ethernet 100 megs should be a cost of 1. That's what it says in my Cisco press book. It is. A 100 megabit link is always 1, or should be 1, unless you set it somewhere different. These links right here, they are fast Ethernet, fast 00. But if you look at the interface, you'll see something interesting. This is a GNS3 thing. So if you show interface fast 00 on either R2 or R1 and pipe I duplex. So just give me the line that has duplex in it. You'll see that it picked 10 megs a second. Now the interface itself, it's 100 meg. You can go up to 100 meg, but it picked half duplex, 10 megabit. So how many of you think that if I go on both sides and I set the speed and the duplex correctly, that cost of 10 should turn into a cost of 1? Yep. Yeah, the auto negotiation failed. Basically, normally in real life it'd work, but this case it didn't. So no problem, not a problem at all. Interface fast 00, speed 100, duplex full. Set that on both sides. Speed 100, duplex full. So now if I show IP OSPF interface brief, yeah, okay, so now our cost is it's gone down to 1, which is what we would expect on a fast Ethernet link. So the cost is based on speed. We can manually change the cost on a particular interface if we want. And it's coming up on 7:30. So I think what we'll do is we'll do this. We'll manually change the cost and then we'll call it a night. Now, why would you manually change the cost? I'll give you a good example. You're an ISP. you've got you've got another router here. So let's say your network looks something like that. And you got a rack of servers here, connected something like that, let's say. You want this link right here. You don't want traffic to go over this link towards this server. So you don't want traffic to go there, but you still want traffic to hit the server. You want it to go around like that. But you don't want to shut the link down. It's bad. You want the link to still be up, but just say traffic going that way, no bueno, don't want it. So here's where we could say IP OSPF cost. We change the cost. Add, let's say 1,000 to it. So if you do that, you're going to say, whoa, change that to 1,000. All of these are still 1. 2 is definitely going to beat 1,000. So your traffic's going to not instantly, but in a moment, after everything converges, it's going to route around the other way. So it's a very quick way of rerouting traffic. So in our instance right here, where it's just a bunch of loopbacks and 2 routers, nothing's going to reroute because we only have one way of getting there anyways. But if we go to R1 and go into one of our loopbacks, IP OSPF cost 10,000. Now if we show IP OSPF interface brief, you'll see that loopback 0 has a cost of 10,000. And if I go to R2, that change is also going to be reflected. Show IP route, OSPF, pipe I, capital O. And so we have loopback 1, or loopback 0, with the IP address of all ones. He is 10,001. It's the cost of the interface and how you got through to the other side. So this guy right here, that's 10,000. This guy is 1. 10,000 plus 1 is 10,001. Okay, any questions about what we did with changing the cost, having the speed influencing the cost? It's basically, it says, okay, if you're 100 meg, you're going to be 1. If you're 10 meg, it's going to be 10. Drawbacks of OSPF, mainly it's going to be in CPU usage. If you have some old routers, if you have new routers, not a big deal. But when you have convergence, a lot of stuff has to happen in the background. If you don't have it tuned to where you have areas and stubs and things set correctly, it can get ugly. There is a protocol out there that people like in certain instances. ISIS can be much simpler. I've seen people talk about how OSPF crumbles because the company threw everything into Area 0 and they were running SAT links everywhere. Probably not a good idea, because when things go down, which will happen often with a SAT link, not so cool. Also, you'll learn later that this whole business with Area 0, so right today we just did single area OSPF. When you start doing multiple area OSPF, connection to Area 0 becomes very, very important. But you're going to run into that in later weeks, later sessions. Speaking of CPU usage, if you don't know how to find it, command on the router, show proc CPU. Now if you do this, this gives you, it's kind of like a task manager in Windows. It shows you everything with percentages and all that. I find the easier, the better way to do it, show proc history. And show proc history, reading this is kind of interesting if you don't know how. I think I have a video about it. Let me just check. I thought I made a video about it. If not, I'll make one. But show proc CPU history, this shows you last 60 seconds, last 60 minutes, and last 72 hours. And this is the percentages. And what you see up here is the decimal format. And you'll see like stars going up. So right now this isn't too exciting. Oh, right here, I got 3 stars going up, and it went up to 27% just momentarily. It's not a big deal. So usually if your router's at 10% or less, it's pretty good. If you see momentary spikes to 100, not a big deal. But if it's always pegged at 100, something probably should be looked at. All right, any questions? Okay, so I'm going to stop the recording. We will continue for a little bit if you want to ask any questions off mic, but let me just stop the recording.